Well, hello and welcome to our third Thursday webinar. I am Tom Sandry, and today we're going to be talking about testing for partial discharge, exploring online techniques. So, without further ado, let's get started. Predictive maintenance techniques, or PDM techniques, are designed to help determine the condition of in-service equipment in order to predict when maintenance should be performed. Now, this approach promises cost savings over routine or time-based preventative maintenance because tasks are performed only when warranted. The main promise of predictive maintenance is to allow convenient scheduling of corrective maintenance and to prevent unexpected equipment failures. The key is getting the right information in the right time. By understanding how assets are aging and knowing which equipment needs maintenance, maintenance work can be better planned, spare parts, people, etc. And what would have been unplanned stops are transformed to fewer, more focused, planned stops, thus increasing plant availability. Other potential advantages include increased equipment lifetime, increased plant safety, fewer accidents with negative impact on environment, and optimized spare parts handling. PDM is a growing opportunity within many organizations, and several service companies are beginning to pursue service offerings to meet this need. Now, many of Protec Equipment Resources clients conduct maintenance service during large plant outages. Now, this is a wonderful opportunity to approach predictive maintenance services such as online PD surveys. Prior to the outage, the service company can conduct an online survey to obtain an early detection of the status of the insulation system. If issues are found, they can then focus time and effort during the outage to resolve these issues. This is also a value added in the final report offered to the client, where the service company can demonstrate their value in a as found and as left report. Now, partial discharge testing plays a critical role in determining the health of electrical assets and ensuring maximum uptime. Partial discharge testing provides reliability managers with the critical information to target maintenance resources to the areas that require attention. As with any diagnostic technology, however, an understanding of the technology and a logical approach to implementation is necessary to render an effective program. Now, partial discharge is a localized electrical discharge that only partially bridges the insulation between conductors and which can or cannot occur adjacent to a conductor. Now, this was a quote taken directly from the IEC 60270 document. Now, in our example here, we show a cable where we have the metallic or the shield earth, a defect in the form of a void, which is within the insulation of the cable, and the conductor of the cable. Now, when the voltage stress exceeds the breakdown strength of that portion of the insulating material, a partial discharge begins and continues to deteriorate that insulation. When partial discharge occurs, various physical and chemical changes may happen, which produce emissions that we can detect, localize, and characterize to provide the information needed to prevent insulation failures of medium and high voltage electrical equipment. Partial discharge occurs in solid, liquid, and gaseous insulation mediums. PD can also occur in the form of corona, surface tracking, or floating electrode, metal-to-metal discharges, causing degradation of the insulation. Now, once partial discharge begins, it will always get worse. The NFPA 70B the recommended practices for electrical equipment maintenance, states that insulation breakdown is the #1 cause of electrical failures. So let's take a look at some of the types of partial discharge. First, the void discharge. This type of discharge is typically found by manufacturers' defects in solid insulation. It can be found in cables, bushings, GIS junction insulation. Void discharges are highly destructive to insulation. And voids typically continue to grow until failure. If a partial discharge is discovered, the insulator should be replaced. Number 2, corona discharge. Corona discharge is one of the 5 distinguished types of partial discharge. Example, breakdowns caused by high voltage, which does not cause a short circuit. Corona discharge is a current flow, usually in the air, from a discharge electrode which is under high voltage. High voltage is a source of air ionization, which creates plasma around the electrode. It is ionized matter containing electrically charged particles. The resulting ions carry the load to places of lower potential. The discharge is invisible in daylight, as most of the radiation generated is in the ultraviolet range, invisible to the human eye, and therefore the development of ultraviolet radiation detectors becomes a valuable complement to acoustic-based detection methods. In addition to corona discharge, the least harmful of partial discharges, there are surface discharges, related mainly to contaminated insulator surfaces and internal discharges caused by degradation of internal insulation. And that brings us to number 3, surface discharge. Discharge along the surface of insulation can be very destructive. This type of discharge is known as surface tracking, usually caused by contamination or weathering of insulator surfaces. It is different from corona because it tends to track to ground metal. Corona discharges to water molecules in the air. Corona conditions can evolve into surface PD as surface contamination worsens and the discharges become more severe. This can happen on any medium and high voltage equipment. Surface discharges most commonly happen when the dielectric strength of the insulation breaks down in high humidity environments or when poor maintenance and cleaning of equipment lead to this phenomena. Moisture intrusion is also a common cause of surface PD. Number 4, the floating discharge. Floating discharge occurs when an exposed load-carrying conductor is exposed to another conductive surface of different potential, not bonded or connected to that conductor. The types of floating discharge may include metal to insulation or metal to metal. This type of discharge is commonly caused by installation assembly errors, poor positioning, and clearances of conductive elements and poor handling. Floating discharge is a very common type of PD. And finally, number 5, particle discharge. This occurs in GIS, SF6 gas, and oil-insulated transformers. Particle discharges are caused when conductive particles and impurities are left inside the insulation system. The activity occurs when partial discharge jumps from particle to particle. Purifying and processing the oil or SF6 is recommended. All right, Online partial discharge testing methods offer the opportunity to discover potential problems under normal operating circumstances. The online approach is a non-invasive, non-destructive, predictive test procedure. These tests can be periodic scans to obtain a quick assessment of your asset, short-term monitoring over longer time periods to provide a more accurate assessment over changing conditions, or continuous monitoring to analyze assets during day-to-day operation to detect deterioration and to raise an alarm or call to action if partial discharge activities reach a critical level. Detection of partial discharge-related faults is based on the principle of determining whether PD activity is at a critical level. Low levels of partial discharge activity are often present in assets at levels which may be considered acceptable. Example, non-critical or unlikely to develop into failures in the short to medium term. When partial discharge occurs, the spark emits energy in several ways, as electromagnetic emissions in the form of radio waves, light, and heat, acoustic emissions in the audible and ultrasonic ranges, and as ozone and nitrous oxide gases. Several discharge detection schemes and partial discharge measurement methods have been invented since the importance of partial discharge activity was realized early in the last century. The various detection methods and sensors provide a means of searching for partial discharge in a wide array of equipment and installation systems. The important item to remember is that there is not a one-size-fits-all solution to partial discharge testing. Using multiple sensing methods ensures that partial discharge activity is always discovered, localized, and characterized. So let's take a look at some of these sensing methods. Let's start with ultra-high frequency or UHF sensors. Now, every time a partial discharge event occurs, electromagnetic waves are transmitted from the site of the defect. This emission may also be called RFI or EMI, radio frequency interference or electromagnetic interference. The partial discharge emission is a broadband electromagnetic emission which can range from the upper radio frequency range up into the microwave range. The UHF range from 300 MHz to 1500 MHz is a typical bandwidth to probe for partial discharge defects in medium and high voltage power systems. All types of partial discharge will produce electromagnetic emissions in the UHF range. In most cases, the UHF emission is detectable with the UHF sensor. The UHF pulses are going to be emitted from the site of the PD defect and will spread in all directions through air and through most materials. However, the signal cannot travel through metal. Metal enclosures will shield the UHF emission. The signal can escape through tiny cracks, gaskets, and seals, and then spread out into the air. The pulses will occur at or near the positive or negative peak amplitudes of the AC sine wave. Thus, the UHF pulses will occur with intervals roughly equal to 1/2 the AC cycle time. Now, for 60 Hz, 1 divided by 60 equals 16.66 milliseconds. 16.66 milliseconds divided by 2 would be 8.33 milliseconds. And for 50 Hz, 1 cycle would be 20 milliseconds. 20 milliseconds divided by 2 would be 10 milliseconds. To prove that UHF could be from a PD activity, we can show that there is a 180-degree separation, 8.33 milliseconds or 10 milliseconds, between the UHF pulses. This is a function of time-resolved or phase-resolved measurements. These phase-resolved measurements are made in real time and serve as the basis for quick partial discharge detection in the field. Now, in some cases, such as inside a power transformer, the UHF emission may be completely shielded by sealed metal enclosures. Fortunately, the UHF signal will also induce a high-frequency current pulse onto the ground of the apparatus. The high-frequency current pulse will be detectable with a high-frequency CT, or HFCT. And that's a perfect segue into talking about the HFCT. Excuse me. When partial discharge occurs, there are small current pulses that are induced onto the ground shield or case ground. These pulses will travel dozens of meters along the ground grid in the form of high-frequency current pulses in the range from 500 kilohertz to around 50 megahertz, usually centered near 10 megahertz. High-frequency current transformers are a reliable method to measure these high-frequency PD pulses. These pulses spread out onto the ground grid like ripples in water. They are especially useful for quickly detecting or testing for internal PD in a large area, such as an entire power transformer or an entire cable, or even an entire substation. The HFCT sensor has a split core, and so it simply clamps around a lower resistance grounding lead. HFCT sensors have a distinct advantage of being able to detect partial discharge signals on cables from long distances up to a kilometer away. Now, this limit depends on the type of ground shield and the strength of the PD pulses. Now, this means that multiple PD signals and noise signals can also be detected from many points on the ground grid where a grounding lead is exposed. In cable PD testing, the localization of PD via the HFCT sensor is achieved by determining the time difference between the arrival of the initial PD pulse and the reflected pulse which has reflected off the opposite end of the cable where you're testing. The speed of the pulses on the ground grid is like the speed of light. Exact signal speeds are known for various cable types. Knowing the speed, the cable length, and the time difference of arrival between the initial pulse and the reflected pulse enables the calculation of the distance to the partial discharge. Now, online cable PD testing instruments many times will have functions to identify these pulses and perform distance calculations. Now, a couple items, though, to mention about the use of the high-frequency current transformers. This test requires the attachment of high-frequency CTs to the metallic cable shields. This presents several safety risks and is considered energized work. To perform this task, the technician must enter the restricted approach boundary of the energized service. Depending on the layout of the cable landing, restricted or blind reaching may be required. Now, this is obviously a violation of the NFPA 70E requirements for work involving electrical hazards. So, the challenge in performing the online partial discharge test on energized electrical power cables is getting the high-frequency CT connected safely. Well, perhaps the best solution is to use the engineering controls from the hierarchy of risk control methods. Now, one engineered approach would be to pre-install the high-frequency CTs into the cable landing compartments. The coax cables can be safely routed along the inner panels of the compartment and then brought out through a bulkhead adapter. Testing can then be carried out safely at any time by simply connecting the scanning equipment to the test connector on the bulkhead adapter. Now, another approach might be to bring the cable shields out of the cable landing compartment. All right, next let's talk about Airborne. ultrasonic sensors. Now, airborne ultrasonic, parabolic dish concentrator, or ultrasonic extension wands. Each time a partial discharge event occurs, an ultrasonic emission is transmitted from the site of the defect. The emissions are typically in the ultrasonic range from 20 kilohertz out to around 300 kilohertz, and may also extend lower into the audible range. If an insulation defect is close to the surface, then the ultrasonic signal will spread out and become airborne. The airborne ultrasonic signal may be detected by one or more of the three types of airborne ultrasonic sensors which are commonly used. An extension wand can be used to listen in hard-to-reach seams of switchgear cabinets or other enclosures. Another type is the parabolic dish concentrator, which is used to extend the distance range of the ultrasonic microphone. The parabolic dish is ideal for checking bushings and insulators for surface tracking and harmful corona. When airborne ultrasonic signals are detected on exposed insulator surfaces, the parabolic dish enables very quick and precise pinpointing of the partial discharge location. Airborne ultrasonic is best for detecting corona and surface tracking. Floating electrode PD will also produce a weak airborne ultrasonic signal. When airborne ultrasonic signals are detected within enclosures, it is not immediately possible to determine the exact location of the partial discharge. By using multi-channel PD receivers, multiple ultrasonic contact sensors can be used to triangulate the signal origin. All right, let's talk about an acoustic emission or AE contact sensor. The AE contact probe is ideal for detecting and localizing partial discharges in fluid dielectrics such as oil and SF6 gas compartments. This is sometimes called in-tank testing. Each time a partial discharge event occurs, an ultrasonic emission is produced at the site of the defect. If the defect is inside a sealed equipment, such as a transformer or SF6 compartment, the signal will usually not become airborne. Fluid and solid dielectrics such as oil, SF6, and resins will permit ultrasonic PD signals up to around 300 kilohertz. However, air cannot permit ultrasonic signals higher than roughly 80 to 100 kilohertz. To use the AE ultrasonic contact probe, it is best to apply a high vacuum silicon gel to the contact probe to bridge the air gap between the exterior of the tank and the contact sensor. This gel will conduct the PD signal from the exterior of the tank onto the ceramic head of the AE contact sensor. Precise PD localization can be achieved by using 3 or more ultrasonic contact sensors to triangulate the exact source. This is especially useful when a transformer is producing acetylene and the engineer needs to know exactly where the problem is before scheduling a maintenance outage to drain oil and go inside. Another important application of ultrasonic localization is in SF6 gas insulated equipment. All right, the next we're going to talk about is the transient earth voltage or TEV. Now, partial discharges in medium voltage power equipment will produce induced radio frequency signals, which are sustained and can be detected at the surface of medium voltage enclosures, such as metal-clad switchgear, manholes, and metal enclosures. TEV signals spread out quickly on the ground plane. For this reason, it is very difficult to locate the origin of a TEV signal. PD from overhead can induce a TEV or TEV signal on an entire line of switchgear. The TEV sensor is a type of capacitive coupler which is built into the main PD detection unit. The TEV sensor is reliable for indicating most types of PD in metal clad switchgear, but it also responds to noise from lighting systems, battery chargers, variable frequency drives, LEDs, and large motors. Void type PD will typically not generate much TEV range signal. Also, PD inside of fluid dielectrics such as transformer oil will not produce a detectable TEV signal. It is important to use UHF, high-frequency CTs, and ultrasonic sensor data in synthesis with the TEV in order to see the whole picture and draw an accurate conclusion about the asset's insulation health. All right, now let's talk about UV radiation. Corona discharges generate the electromagnetic spectrum in the range of 200 to 405 nanometers. Solar radiation also contains, in addition to visible light, both infrared and ultraviolet radiation. Using an appropriate filter, wavelength ranges from 240 to 280 nanometers, we can suppress UV radiation generated by the sun, so the camera may operate well in daylight without interference. And now let's take a look at high voltage capacitive couplers. These devices are typically installed when the equipment is de-energized and then can be used for online monitoring and testing of partial discharges. These are electrical pulse sensing devices that are picking up pulses created by the occurrence of partial discharge. These couplers can fall into one of three frequency ranges. In the low frequency or LF range, they offer excellent effective measurement range distance, but are very susceptible to noise and disturbances. In the high frequency or HF range, they are less susceptible to noise and disturbances. The trade-off, though, for better signal to noise is the effective sensing distance. And in the very high frequency range, they provide a good signal to noise ratio and are therefore less susceptible to noise and disturbance, however, with the trade-off of effective sensing distance. Now, when using UHF, HFCT, or ultrasonic sensors, we use a concept called phase-resolved analysis. Consider the sensor that you're using. It has a bandwidth that spans portions of the radio frequency spectrum or the ultrasonic spectrum. There are all kinds of other signals and other energy in that bandwidth that has nothing to do with partial discharge. It's what we call noise. Example, telecommunication signals can be a form or an example of noise. Now, phase-resolved partial discharge patterns are a method of comparing the incoming signal to the AC power frequency. The PRPD charts are shown in real time. The horizontal x-axis is the phase angle of the power system under test. The x-axis is labeled from 0 to 360 degrees. This is the same thing as a 0 to 16.66 millisecond. This is the time it takes for one cycle of the AC power frequency. The vertical axis, or y-axis, represents the amplitude of the signal. The amplitude depends on the strength of the signal and on the distance from the sensor to the PD event. Now, we know that partial discharge signals are produced as the sine wave reaches a positive or negative peak or trough or peak voltage stress. The sine wave peaks and troughs are exactly 180 degrees apart, 16.66 milliseconds divided by 2, or every 8.3 milliseconds. The partial discharge pulses continue to arrive with intervals equal to 8.3 milliseconds or multiples of 8.3 milliseconds, 180 degrees apart, with some fluctuation due to partial discharge inception and extinguish points. As the insulation deteriorates, the partial discharge will begin earlier and they will extinguish later as its ability to withstand the voltage stresses diminishes. Meanwhile, all the other noise and other signals in the detection bandwidth or the sensor will arrive at random time intervals that are not equal to 8.3 milliseconds. Noise arrives at random points along the x-axis, whereas partial discharge pulses arrive at 180-degree intervals. Now, in addition to discovery and identification of PD activity, the PRPD method can be used to determine the type of partial discharge activity that is occurring. Each type of partial discharge has a certain pattern in the distribution of pulses. The charts that we will review show the typical patterns for each type of partial discharge. So, here's an example of floating electrode partial discharge. The UHF signal is very high and consistent in amplitude. The signal spreads across a wide portion of the half cycle for both positive and negative half cycles. Here we see an example of a void discharge. The UHF emission is lower in amplitude than a floating electrode. The distribution of pulses is less dense than surface or floating discharges. The pulses span a wide portion of both positive and negative half cycles. Here we see an example of corona discharge. The UHF pulses from a corona discharge are low in amplitude and only occur on the negative half cycle as electrons leave the conductor to ionize the surrounding air. And here we see an example of surface tracking discharge. UHF pulses resulting from surface tracking are typically much denser on the positive half cycle as electrons move from ground to the conductor. And here we see particle discharge. The UHF emission resulting from particle discharge are often scattered across a phase because it usually happens on multiple phases simultaneously. This type of partial discharge may be difficult to distinguish from noise. Dissolved gas analysis results and SF6 testing may provide proof that the PD exists. Multi-channel diagnostics can be used to locate the source. Acoustic fly charts can also help determine if the signal is a particle discharge. All right, now let's talk about ultrasonic partial discharge signal analysis. Now, phase resolve techniques are also used to analyze ultrasonic PD signals. The analysis techniques are the same for both airborne and ultrasonic contact testing. There are several modes which can be used to analyze the signal. For example, waveform mode is shown here. The x-axis of the image is spanning 2 cycles of the power frequency, hence the notation 2T. Partial discharge activity will produce an ultrasonic emission each time the sine wave reaches a positive or negative peak. This means that in a 2-cycle time interval of approximately 33 milliseconds, there will be 4 ultrasonic pulses. The PD pulses have a short rise time and short duration. The peaks are tall and sharply rise above the noise floor. Typically, We consider the activity to be severe if the amplitude reaches greater than 10 dB at full gain setting. Now, it is possible that core vibration in a transformer can produce an ultrasonic signal, which are very similar to partial discharge. We can use several strategies to determine if the signals are PD or only vibration. We can compare the width of the peaks to the height of the peak. The PD signals have a narrow width and a tall peak. The vibration signals have a wider base and a wider peak, which may split into multiple peaks. Amplitude emission, or AE amplitude, is also used to compare the 60 Hz and 120 Hz resonance. If the 60 Hz resonance is approximately equal to the 120 Hz resonance, then the signal is most likely vibration or disturbance. A phase spectrum mode is also used to compare the incoming signal to the power frequency. It's like phase resolve PD patterns for UHF and HFCT testing. Vibration signals will have very consistent timing in sync with the phase and very consistent amplitudes. The peak amplitude will be very close to the average amplitude. The partial discharge signals will typically have more irregular timing and varying amplitudes, yet they will still be mostly synchronized with phase timing. Finally, the most competent way to be sure if you have a partial discharge or a vibration is to compare the ultrasonic signal with the high-frequency CT or UHF signals simultaneously. For this, you need a multi-channel diagnostic unit to see the relative timing of ultrasonic and electromagnetic pulses. If the ultrasonic emissions are in perfect synchronization with the high-frequency CT pulses and the UHF pulses, then it must be partial discharge. Vibration will not produce electromagnetic pulses. AE phase spectrum plots the phase angle versus amplitude. The image shows the AE phase spectrum of a surface tracking partial discharge activity. The pulses have varying amplitudes. The pulses are different on the negative and positive half cycles. AE phase spectrum of mechanical vibrations. The ultrasonic pulses have consistent amplitudes. The signals are the exact same on the negative and the positive half cycles. All right, next let's talk a little bit about partial discharge conditions. For instance, condition 1, partial discharge activity is not present, or it is at a subcritical level. The results provide assurance that partial discharge-related faults are unlikely to develop at present. In a condition 2, partial discharge activity is at a level which indicates that a fault is developing and requires further investigation or monitoring. Condition 3, a partial discharge activity is at a level which indicates that a fault is at an advanced stage of development. The fault is likely to cause imminent failure, and the asset may be energized to an extent that is dangerous to personnel. This level of partial discharge activity indicates the need for immediate investigation and intervention. Now, here we show some sensor utilization during a switchgear survey, where UHF sensors can be used anywhere where we have openings in the metal enclosures. Also, acoustic emission and ultrasonic contact probes can be used along the cabinet doors and panels. Also, we can take transient earth voltage measurements along the panels. Here we see sensor utilization in GIS surveys. Again, the UHF sensors can be used anywhere where we have gaskets or fittings, where the ultra high frequency signals can escape the metal cladding. Also, we can use in-tank testing methods, utilization of the AE contact sensors. For transformers, we can use UHF sensors, scanning and monitoring along bushings for any internal partial discharge. We can also use the parabolic dish and ultrasonic along the bushings for any signs of surface tracking or corona. We can use the AC contact sensors for in-tank testing, and also a UHF adapter sensor for the drainage plugs. Also, we can take HFCT measurements along the ground straps. For substation yards, we can use a variety of sensors. We can use corona cameras for detection of the UV radiation. We can also use the airborne ultrasonic techniques and the parabolic dishes. Along the ground straps, we can also use the high-frequency CTs and the ultra-high frequency sensors. Excuse me. Now, let's talk a little bit about analysis and recommendations. Many factors must be considered when assessing insulation quality, such as age, visual appearance, environmental conditions, partial discharge magnitude and partial discharge rate of change, partial discharge signature, and comparison of this data to similar insulation installations. Collectively, these factors will provide useful insight to the present condition of the insulation and its projected lifetime. Partial discharge testing is utilized to determine insulation condition and an early warning of impending failure. However, many sources of background noise can be present, including conducted noise from process loads, radiated noise from nearby electronic equipment or radio transmissions, and actual PD reflections coupled to the test object from other components. Partial discharge testing is one of the best tools available today to predict and prevent electrical failures. Reliability statistics indicate that up to 85% of all insulation failures can be detected with this technology. Now, since electrical insulation failure mechanisms are very complex phenomena, there is a possibility that an electrical component may fail before the next annual partial discharge survey is conducted. Now, some possibilities that can occur, this would include human error or accidents that may occur, lightning, transients, or switching surges, mechanical failure in the equipment, insulation damage due to rodents or other pests. Also, the defect can be at an advanced stage. The defect may already be conducting through a carbon path, which acts electrically as a resistor, and no abnormal signals will occur. The partial discharge source may be inactive at the time of the test. It can contain defects that may vary with humidity, temperature, or other conditions. Also, crossing polyethylene cable may contain water trees. For the most part, these water trees do not present an immediate concern. However, certain electrical events such as lightning or switching surges may initiate the water tree into a rapidly occurring electrical tree and thus a fault. Supplemental offline tests such as tan delta can be performed to evaluate cables for contamination such as water treeing. Also, periodic monitoring should be considered for all critical circuits. Now, remember, online partial discharge testing, much like infrared scans, is a snapshot captured in a moment of time during operating conditions. Therefore, it is recommended to capture the operating conditions at the time of the scan. Data that will assist in your trending and analysis include: what is the operating voltage and the load conditions during your scanning? What are the environmental conditions? What type of insulation are you scanning? Is it an extruded dielectric, a laminated dielectric, or possibly insulating liquids or gas? Were you able to detect the location of the defect? Now, for some insulation systems, action may be immediate. In other cases, you may need to trend the condition and the rate of change. Further tests may also be required to determine the extent of deterioration. In liquid insulation systems, you may wish to obtain a fluid sample and conduct a dissolved gas analysis, or DGA. In gas insulation systems, you may wish to conduct a humidity and purity analysis. And that concludes our webinar today on online partial discharge techniques. As always, I do appreciate you taking the time out of your busy days, joining us on our Third Thursday webinars. Again, I do truly hope that the information that you gather through these webinars are useful to you in your career growth and in your day-to-day test and maintenance activities. So, without further ado, let's get to those questions and answers.